Hi everyone, this is Liang Yang from Michigan State University. Here I will present our work, Understanding Power Consumption of NB-IoT in the Wild, Tools and Large-Scale Measurement. This is a joint work with my advisor Dr. Xing and many other collaborators. To begin with, let's take a glimpse of the NB-IoT technologies. It supports massive connection with low device power consumption, enabling a wide range of applications, such as smart metering, smart parking, environmental sensing, smoke sensing, and more. After 4 years evolution, development, and deployment, it is launched globally with more than 65 network operators in more than 50 countries. The NB-IoT standard has a 10-year battery life estimation. However, until now, the NB-IoT energy performance in the wild is not well understood. This is due to 3 reasons. First, unlike LoRa and many other low-power wide area networks, NB-IoT is a closed cellular system where the researchers and the developers do not have access to the base station. Second, heterogeneity exists in the network, including module variants, multiple network operators, and the application scenarios diversity, which presents a high barrier for the NB-IoT study in the wild. Finally, the lack of diagnostic tools for large-scale measurement hinders the understanding of the NB-IoT network. In this work, we design a system for large-scale NB-IoT energy consumption benchmark. Then we conducted extensive field measurement lasting for 3 months, collecting more than 49 gigabytes of measurement data. We identified several major problems in the existing NB-IoT networks, such as high energy imbalance and heterogeneous coverage. Next, we break down the energy to diagnose the causes for these problems. Based on our findings, we propose several optimizations to the node energy performance. Before our design, we would like to provide the primers of the NB-IoT technologies. To upload a packet, the node, also known as user equipment or UE, first need to establish the connection with the base station, also known as eNode B. To achieve this, the UE sends message 1 and message 3 to the eNode B. Then the UE, when the UE is in the connected state, it sends the data package to the eNode B. Then, before the UE enters other power-saving modes, it releases the connections. NB-IoT adopts open-loop power control by specifying 3 coverage levels, also known as ECLs. Specifically, ECL 0, 1, and 2 applies to good, moderate, and bad channel conditions, respectively. The eNode B can assign each ECL with different radio access resources to direct UE behavior, and the 3 levels are separated by 2 thresholds according to RSRP, which is reference signal receive power. When the UE is about to transmit a packet, it measures the RSRP and compares it to the threshold to design its coverage level. Then it uses the radio access resources in that level and calculates TX power accordingly. The next part is our NBScope design, a system for large-scale NB-IoT field measurement. To benchmark the UE power consumption in the wild, our design should meet the following requirements. First, we need in-depth diagnosis of energy efficiency, which means that we will measure the energy consumption of the NB-IoT modules, as well as collect and analyze the module radio access traces from the module debug logs. Second, our system should support large-scale measurement while resolving the NB-IoT module variance. It should also be lightweight to conduct the measurement on a large scale. A challenge we face is the various NB-IoT modules available on the market. To resolve this module heterogeneity, NBScope adopts layer architecture with a module show board and a mainboard design. We designed the show board by first selecting a list of popular commercial NB-IoT modules. Then we analyzed their connectivities and identified several set of pins to be interacted with, such as power supply, SIM card interface, serial ports, and so on. They are aggregated into 2 rows of pin headers, as shown in the red circles. Currently, we design 7 types of show board supporting 9 different types of modules. Such a design also allows easier integration of other modules. The embedded board is lightweight and has all the major functionalities for field measurements. By plugging in the show board, we have an NB-IoT node ready for the measurement study. All the radio access traces and the energy profile will be written into the onboard storage and will be analyzed offline. Another feature of NBScope is the trace fusion. First of all, we can obtain a list of radio access messages by decoding the raw debug logs from the modules. Then we synchronize the messages with the current profile such that the causes of the energy variation can be studied in detail. The next part is our large-scale NB-IoT measurement study. First, we present the statistical analysis from the collected data. Then we break down the energy consumption by radio access procedures and diagnose the causes for the problem we find. Finally, we estimate the battery life of the NB-IoT UE based on the measurement results. Our measurement study lasts for 3 months in 3 regions, covering 3 network operators using 6 types of NB-IoT modules. We selected 5 application scenarios in our study, which can emulate a wide range of applications in the real world. There are more than 49 gigabytes of data collected from over 1,200 locations. By extensive statistical analysis, we identify several problems in the existing NB-IoT network. First of all, we observe high energy imbalance among the nodes, where the worst nodes can consume up to 75 times higher than the normal nodes. We will explain this in 3 different perspectives, including application scenarios, network operators, and the module variants. Next, we notice that the long tail energy takes a significant portion of packet energy. The third problem is the heterogeneous coverage level, where the resource allocation is significantly uneven. Yet, the ECL decision mechanism is oversimplified. Let's take a look at the NB-IoT UE power versus location and network operators. From left to right, the average power consumptions increase. This is foreseeable because outdoor environment usually has better signal qualities. However, one thing that surprised us is that the indoor parking UEs has higher energy consumptions than water meter UEs. The reason is that there are multiple micro cells deployed in the basement to augment the coverage. However, for the given type of application scenario and the network operator, the energy consumption is highly unbalanced, where some nodes drain powers several times or even tens of times higher than other nodes. This will result in highly unpredictable node lifespan in the IoT applications, which may lead to data loss or high maintenance cost. Next, we noticed that the nodes in different network operator has large energy consumption variance. One of the reasons is that these network operators have different network configurations and deployment scales. We also noticed that the module differences have noticeable impact on the energy performance. The nodes differ in their maximum current in a packet. For example, the maximum current of M1 is 2.2 times higher than M5. In this case, the energy consumption deviates significantly. We showed that the energy consumption of different modules in our data set on the right, decomposed by the coverage level. We can see that some packets can be several times or tens of times higher than the average energy drain, mainly due to excessive number of retransmission. Besides that, ECL2 usually have significantly higher energy than ECL0 and 1 for almost all the packets. Since the nodes in NB-IoT applications are usually stationary, their ECL usually remains in the same in the long term, which is one of the causes for energy imbalance. To understand the energy consumption of each of the radio access procedures and the reason why ECL has a higher energy than ECL 0 and 1, we decompose the current profile to understand the contribution of different radio access procedures in the packet cycle. We show the overview on the left. The UE first transmits the packets by radio access. Then it stays in the connected state for a long time, determined by a timer called inactivity timer. The purpose of this period is to allow the UEs to transmit either potential packets or receive downlink packets if there is any. However, currently the network operator set a timer as 20 seconds, which causes high long-tail energy waste in the node. Let's take a closer look at the radio access part. We find that ECL2 has higher energy than ECL0 due to several reasons, such as higher transmission power, extra message 3 repetition, and longer transmission time. The table shows the mean power consumption by the radio access procedures. We can see that the long tail power due to the large inactivity timer occupies most of the energy consumption, regardless of the coverage levels. If we ignore the inactivity period, the message 3 energy makes the most difference among the ECLs. Since ECL plays an important role in the UE energy behavior, we plot the ECL ratios for part of our application scenarios. We conclude that ECL is probably the dominant factor that affects the power consumption other than the long tail energy. By analyzing the radio access trace, we find another issues in the ECL decision mechanism, which may not be well adapted to the dynamics in the wireless channels. We identify high energy imbalance and the long tail energy in the deployed network. Next, we investigate the resource allocations in ECL. We acknowledge that the message need additional repetition to overcome the path loss in the bad signal condition. But the question is that, is this investment worthy? To answer that, we compare the message 3 repetition with the data block repetition in the same packet. The difference between message 3 and the data block is that the repetition of data blocks are dynamically scheduled, while the message 3 repetition is a fixed number in each ECLs. We found out surprisingly that message 3 repetition is greater than data repetition in almost 2/3 of the packets. So if we can use less repetition to transmit the data, why we need so many repetitions in message 3. To conclude, the scheduling message, which is message 3 in this case, is excessive. Based on our measurement results, we estimate the UE battery life under different ECLs, inactivity timer, and daily traffic. The best case we can achieve is 6.3 years, where the inactivity timer is assumed to be 3 seconds, while the traffic is 1 packet per day. However, with the same traffic, but the ECL2 environment and 20-second inactivity timer, the battery life is shortened by 35% to 4.1 years. Yet this is an optimistic estimation, because in real-world scenarios, many other factors can affect the battery life. Next, we propose our strategy to optimize the energy performance for NB-IoT nodes. We note that the period before the UE entering inactivity state, which is controlled by inactivity timer, has significant impact on the energy consumption. So what is the optimal inactivity timer? In reality, the UE can go to sleep after receiving the packet from the server. Therefore, we measure the packet round-trip time, which starts from uploading the packet to receive the feedback from the application servers. From the figure on the right, we see that if the timer is set to 8 seconds, the downlink reception of ECL 0 and 1 UEs are now compromised, while 60% of the tail energy can be saved. If we further decrease the timer to 4 seconds, about half of the ECL2 nodes will not be able to get the downlink packets. But this can save 80% of the long tail power of the nodes. So there's a trade-off, and the timer value should be set carefully by the network operator empirically. Next, we find the optimal message 3 repetition number with a software-defined inode B testbed. We arrange 4 nodes in ECL2 environments with a decreasing RSRP. In the first experiment, we cut the repetition to 1/2. We noticed that the message 3 retransmission rate is similar to the 32 repetition case. If we further reduce the repetition to 1/4, the node number 1 and number 2 are not affected mostly, while the energy cost is reduced. However, node number 3 and number 4 cannot benefit from this because the message 3 retransmission rates increase. Overall, there is much room in optimizing the message 3 repetition count. By optimizing both inactivity timer and the message 3 repetition, it is possible to save up to 81% of the energy globally. To conclude, we designed NBScope, a system for large-scale NB-IoT performance benchmark. We conducted extensive measurements and identified 3 problems in the existing NB-IoT network, including high energy imbalance, long tail power, and heterogeneous coverage. We propose and validate energy optimization for inactivity timer and message 3 repetition, which can save the UE energy significantly. We envision that by combining the debug logs with packet level measurements, our tool, NBScope, can also be used to study other NB-IoT performance metrics such as reliability, latency, interference, etc. Please find more information in our paper. Thank you.